Okay, in today's lecture we're going to cover our section 13.5 material on the fundamental theorem of calculus. So recall in our last section we had introduced the idea of a definite integral, which represents the area underneath the graph of a function over some x interval. And we saw that the definite integral can be defined as the limit of a Riemann sum, where a Riemann sum was the sum of the areas of a bunch of small rectangles that we were using to approximate the area under that curve. And as we take a limit, as the number of rectangles approaches infinity and their width is shrinking down to 0, we get the true area under the graph of our function. So the examples that we had done in our last section, where we were approximating the area under a curve by using rectangles, showed that it can be a little tedious to calculate or approximate area by using this Riemann sum approach. So the fundamental theorem of calculus is going to give us a much more efficient way to evaluate definite integrals and calculate those areas. So let's take a look at what this theorem says. So here, suppose that f is some continuous function on the interval from a to b, and f is any antiderivative of the function little f. Then the definite integral of f with respect to x over the interval from a to b is found by taking the antiderivative, capital F, at the endpoint b, and then subtracting the value of the antiderivative, capital F, at the left endpoint of our interval a. Now, some notation that we typically use to denote that difference is the following. We would say capital F of x, and then we have a vertical bar after it with a subscript of a and a superscript of b, which are denoting the left and right endpoints of our interval. So again, this notation, if we have a function and then after it we're writing a vertical bar with these values a and b, we're using that to denote the difference f of b minus f of a. So that is, we're evaluating this function at the upper endpoint first, and then subtracting the value of the function at the lower endpoint. So instead of having to evaluate these definite integrals using Riemann sums, or the limit of a Riemann sum, this fundamental theorem of calculus says all we need to do is find any antiderivative of the function f, and then evaluate it at the endpoints of our interval. So let's look at some examples of this. In our next example, we're asked to evaluate a given definite integral. And in part A, we have the integral from 4 to 6 of 4x with respect to x. So, though using the fundamental theorem of calculus, we need to find an antiderivative of this function, 4x. So the antiderivative of 4x using the power rule will be 2x squared. And then we said, in general, we can add any constant we want to our antiderivative to get the most general antiderivative. And then we're going to take this antiderivative that we found, 2x squared plus any constant, and evaluate it from 4 to 6. So we start by substituting in the value of 6 for x. So we would have 2 times 36 plus some constant c minus, we substitute 4 in for x, and we would have 2 times 16 plus c. So let's simplify this. This is 72 plus c minus 32 plus c. So our 72 minus 32 leaves us with 40. And then notice that our arbitrary constant c, and then when I'm subtracting c, will cancel. So I'm just left with a value of 40. Now, in general, moving forward, we will no longer write the constant of integration when we're evaluating these definite integrals. Let's ask ourselves why not. So as we saw in this example, if we include an arbitrary constant c on the end, when we evaluate our antiderivative at the endpoints, in this case 4 and 6, and take the difference, we have these arbitrary constants canceling each other. And of course, that would always happen regardless of what function we were taking the antiderivative of or what our endpoints were. So we no longer need to explicitly write the constant of integration for definite integrals, since that constant will cancel anyway. Now, another reason which we can omit the constant, which is maybe a little more precise, is in the statement of the fundamental theorem. So the fundamental theorem of calculus says to evaluate this definite integral of f of x with respect to x, we're going to take an antiderivative capital F of x where capital F was any antiderivative of our function. So if we can use any antiderivative of the function, let's choose the simplest one where our constant c that we're adding to the end is the constant 0. That is the case where we're not adding any constant onto the end of our antiderivative. So in summary, moving forward for definite integrals, we will no longer write that plus c when we're finding our antiderivative. So let's look at some other ones. In part B, we have the integral from 0 to 1 of e to the 3t with respect to t. So to evaluate this definite integral, the fundamental theorem of calculus says we first find an antiderivative of our function, e to the 3t, which recall would be 1/3 e to the 3t. And we no longer have to write the plus c on the end, since this is a definite integral. So once we have our antiderivative, we're going to evaluate it at the endpoints 0 and 1. So recall we first substitute the upper limit 1 into our antiderivative. So we would have 1/3 e cubed, and then we subtract what we get when we substitute 0 in for t. So we would have 1/3 times e to the 0, which is just 1. So we're subtracting 1/3, or if we want, we could simplify our answer a little bit by factoring out a 1/3, and we would be left with e cubed minus 1. Now, in our next example, part C, we have the definite integral from 1 to 9 of the square root of z with respect to z. So recall that the square root of z is just the same as z to the 1/2 power. So to evaluate this integral, we need to find an antiderivative of our function, z to the 1/2. So using the power rule, we add 1 to the exponent, so we would have z to the 3/2, and then we divide by 3/2, which is equivalent to multiplying by 2/3. So once we have our antiderivative, and recall we no longer need the plus c if we're working with a definite integral. So once we have this antiderivative, we are going to evaluate at the endpoints 1 and 9. So here we have a constant 2/3 out in front, and then if I evaluate 9 to the 3/2, we'll simplify in just a moment, then we would subtract our 1 to the 3/2 power, which is just 1. So we had our constant 2/3, and now let's see how this can be simplified. So 9 to the 3/2 power, or more generally, x to the 3/2 power, is the same as taking x to the 1/2 power and then cubing it. By properties of exponents, recall if you have a power function that's being raised to some power, you would just multiply your exponents. But we mentioned that x to the 1/2 power is the same as the square root of x. So here we would have the square root of x cubed, or in other words, square root of x times square root of x times square root of x. But if I multiply the square root of x by itself, if I take just the product of those first two, I would have x, and then I'm multiplying on the end by the square root of x. So whenever I have a number being raised to the 3/2 power, that's the same as taking that number times the square root of that number. So in the case that we have 9 to the 3/2, we would have 9 times the square root of 9, which is 3. So that value is 27. And then we're subtracting 1. So we have 2/3 times 26, which is 52/3. Okay. So let's look at some other ones. So these next examples are going to illustrate some properties of definite integrals. Now, the fundamental theorem of calculus says that to evaluate a definite integral, we just need to find an antiderivative of the function that we're integrating. And so all of the properties that we had for indefinite integrals, or for antiderivatives, will also hold for definite integrals. So let's review some of these properties. So here in the statement of our theorem, let's suppose that f and g are integrable functions and c is some constant. So the first two properties follow directly from what we've seen for indefinite integrals, namely the integral of a constant times a function is equal to the constant times the integral of the function. So in other words, I can pull a constant out in front of an integral. Property number 2 is also called the sum difference rule, just like we had for indefinite integrals, where the definite integral of a sum of two functions, say f of x plus g of x, or a difference of functions, f of x minus g of x, is equal to the sum or difference of the integrals of those individual functions. So in other words, you could integrate each function individually if you're looking at a sum or difference of functions. Now, properties number 3 and 4 are sort of unique to definite integrals. We can't really think about these properties as having an analog for an indefinite integral. But property number 3 says that if we're looking at the integral of a function, f of x, on the interval from a to b, that's the same as taking the negative of the integral of that same function, where our limits of integration, a and b, are reversed. So if I want to change the order for my limits of integration, say from a to b, moving from b to a, we would just take the negative of that value. So why might we want to do this? Well, typically when you're working with problems in integration, you'll notice, like if we look at our example below, that the upper limit of integration is always the larger number. That's the standard convention for how this thing is defined. So in some cases that we'll see a little later in this section, we might have an integral of the form, let's say 7 to 0 of x squared dx. So here, if our upper limit of integration is less than the lower, we might want to reverse the order of those two. And this property number 3 says, well, in order to reverse the order for the limits of integration, we would just take the negative of the integral, which has those limits of integration reversed. Now, property number 4 says if we're integrating a function f of x on an interval from a to b, we can split this up by first integrating the function on the interval from a to c, and then integrating the same function from c to b and taking the sum of those values. And this property makes sense if we think about the geometric interpretation of the definite integral as area under a curve. So let's say that we have some nice smooth function, say y equals f of x, on an interval from x equals a to x equals b, and I want the area of this shaded region that lies under that curve on the AB interval. So this theorem says, well, I could first integrate from a to c, so take the integral from a to some value c, and we could take the definite integral of our function, which would give us the area shown in blue here. And then we could then add the integral from c to b of the same function. So integrating from c to b would give us the area of this region, and we can see that the sum of those two areas would give us the integral over the entire interval from a to b. So let's look at some examples which may make use of these properties. So in part A, we're evaluating the integral of a polynomial. So it's a sum of a couple of terms. And property number 2 from our theorem says, well, we can find the definite integral piece by piece. Or, in other words, we could find an antiderivative of this function. And we know the antiderivative of a sum is the sum of the antiderivatives. So in this case, antiderivative of 4x is 2x squared, plus the antiderivative of 3x squared is 1x cubed. And then once we have this antiderivative, we can evaluate on our interval from 1 to 3. So we start by substituting the upper limit of integration in for our antiderivative. So evaluating at x equals 3, we would have 2 times 9, or 18, plus 3 cubed, which is 27. And then we subtract the value that we get when we evaluate at the lower limit of integration, in this case 1. So evaluating at 1, we would have 2 plus 1 cubed, which is 1. So we have 18 plus 27, and then we're subtracting 3, which leaves us with a value of 42. Now in part B, again, we're integrating some polynomial function. It involves a sum or difference of a few terms. So using the fundamental theorem of calculus to evaluate this integral, we just need to find an antiderivative of this function. So here, the antiderivative of 6t squared would be 2t cubed, minus the antiderivative of 2t, which would be 1t squared, plus the antiderivative of the constant 1 with respect to t would be 1t. And then we're evaluating this antiderivative on the interval from -2 to +3. So we would have, when we substitute 3, the upper limit of integration, into our function, we have 2 times 3 cubed would be 54, minus 3 squared, which is 9, plus 3. And then we subtract what we get when we substitute in the lower limit of integration, which was -2. So evaluating at -2, we have -2 cubed, which would be -8, times 2, so -16. then minus a negative 2 squared is 4, and then plus a negative 2. So let's see what we're left with. So combining all of our constants, we are left with a value of 70. So let's look at some others, maybe a little more complicated. In part C, we have the integral from 1 to 2 of x to the 6th minus x squared over x to the 4th with respect to x. So we see that it involves a quotient. So recall the integral or the antiderivative of a quotient is not just the quotient of the antiderivatives. So we could try to use a substitution here, but a substitution actually isn't necessary. If we split this fraction as x to the 6th over x to the 4th minus x squared over x to the 4th dx, then this reduces nicely. We have the integral from 1 to 2 of x to the 6th over x to the 4th, which is x squared, minus x squared over x to the 4th, which would be x to the negative 2 power, or 1 over x squared. So now we can find an antiderivative for each piece individually. So the antiderivative for x squared would be 1/3 x cubed, and the antiderivative for x to the negative 2 would be x to the negative 1, and then we're dividing by negative 1. So that will cancel the initial negative that we had out in front, or maybe showing a little more detail from my work here. We got negative x to the negative 1 dividing by negative 1. And then we're evaluating from 1 to 2. So simplifying a little bit, we have 1/3 x cubed. And as I mentioned here, when we're subtracting, and then we have division by this negative 1, that will just change the sign of this term. We get a positive x to the negative 1, which is just 1 over x. And now we're evaluating from 1 to 2. So when we substitute 2 in for x, we have 8/3 plus 1/2. And then we subtract the value that we get when we substitute 1 in for x, which would be 1/3 plus 1 over 1, which is just 1. So let's see what we're left with. We had an 8/3 minus 1/3, which would be 7/3. And then we had a positive 1/2, and we were subtracting 1. So 1/2 minus 1 gives us a negative 1/2. And then getting a common denominator, we're left with 11 over 6. Okay. Now in part D, we have something sort of similar to what we had in part C, but instead of integrating a quotient, we're integrating a product here. We have t cubed minus 1 quantities squared. So we know that the antiderivative or integral of a product of functions is not just the product of the antiderivatives or the integrals. So we can't simply do that. And we notice that this is a composite function, so we might want to try a substitution. But if you try a substitution here, you see that it doesn't work out very well. Certain terms don't cancel in a way that allows you to integrate using substitution. So another approach which we could use here would be to think of this t cubed minus 1 squared as t cubed minus 1 times itself, and then expand that product. So expanding this, we would have t to the 6th power minus 2t cubed plus 1 dt. So integrating term by term, well, the antiderivative of t to the 6th would be 1 over 7 t to the 7th, minus the antiderivative of 2t cubed is 1/2 t to the 4th power, plus the antiderivative of 1 dt would be 1t, which we're then integrating from 0 to 3. So we start by substituting in our upper limit of integration, in this case 3. So for our first term, we have 3 to the 7th power, which using a calculator gives us 2187, and then multiplying by 1/7. Minus, for our second term, we have 3 to the 4th, or 9 squared, which is 81 times 1/2, plus 3. And then we subtract what we get when we substitute our lower limit of integration in for t. Now notice in this case, our lower limit of integration is 0. So if you evaluate this function at t equals 0, you're left with 0. So we're subtracting nothing here. So simplifying our answer by getting a common denominator of 14, we're left with 3,849 over 14. Okay. Now in our next example, part E, we have the integral from 4 to 8 of 2 over x. So recall this is the same as factoring out the constant 2. That's one of my properties of integrals. I can pull constants out in front. And then I'm left with the integral of 1 over x dx on the interval from 4 to 8. Now recall that the antiderivative of 1 over x is the natural log of the absolute value of x. So we have 2 times the natural log of absolute value x, and then we're evaluating on the interval from 4 to 8. So we have our constant 2 out in front, and when we evaluate the natural log of x at x equals 8, we have natural log 8 minus the natural log of our lower value, 4. So now, we could, of course, leave our answer in this form, but if we want to simplify this a little bit, we could make use of properties of logarithms. So in particular, recall that the difference of two logarithms with the same base is the same as the natural log of the quotient of those values. That would be the natural log of 8 over 4, or natural log of 2. Now, I can simplify a bit further still. So this constant out in front, 2, recall we can bring into the exponent for the argument of that logarithm. So where this property typically arises is in the opposite direction. Let's say we have the natural log of x to some n power. That's the same as n times the natural log of x. In other words, you can bring the power out in front. So using that property but in the reverse direction, I can take this constant 2 out in front of my logarithm and bring it into the exponent here. So we have the natural log of 2 squared, or simply log 4. And this answer is equivalent to what we had found here, but is, of course, in a nicer, more simplified form. So let's look at some other examples where we'll evaluate some definite integrals and where our process of finding the antiderivative may require a substitution. So in this next example, we're asked to evaluate the integral from 0 to 4 of x times the square root of 16 minus x squared dx. So here we've got a product of two functions, x and the square root of 16 minus x squared. So we can't integrate using, say, just a sum or difference of terms, as we have been in our previous examples. So instead, we notice that the second part of our integrand involves a composite function, the square root of a polynomial. So anytime that we see a composite function, if we can't use some other approach, it typically suggests using a substitution. So we're going to make a choice for u, the variable that we want to substitute for. And again, it's typically chosen as the inner function in a composition. So in this case, our inner function was 16 minus x squared. Now, once we choose u, our next step is to find the differential of u. Now recall the differential of u is the derivative of u, so in this case, negative 2x times the differential dx. Now, our goal is to take the original integral that we were given, so shown here in terms of x, and rewrite it in terms of u. So what's a little bit different in the case that we've got a definite integral and we're using substitution is we now have limits of integration. I've got values of 0 and 4, but recall that these values were values of the variable x, since we were working with a dx. So if we're going to rewrite our integral in terms of u, I need to know what the corresponding values for u are. So let's start by looking at our lower limit of integration. So if the value of x is equal to 0, that was our lower limit of integration in the given integral, then we need to know what u is equal to. Now remember, u we set equal to 16 minus x squared. So if x is 0, then we just have 16. And we need to also change our upper limit of integration to a u value. So for the given integral, we had an upper limit of x equals to 4. So if x is equal to 4, then we need to know what our u value is. Now u is 16 minus x squared. So if x is 4, we would have 16 minus 16, or 0. So our original integral, that is the integral from 0 to 4 of x times the square root of 16 minus x squared dx, is equal to, well, let's see what we have in terms of u. So our lower limit of integration, x equals 0, we said changes to a u value of 16. So that will be our lower limit for the integral in terms of u. And our upper limit of integration, which was x equals 4, gives us a value of u equals 0. So our new upper limit is 0. Now what we're left with is the square root of 16 minus x squared, which is simply the square root of u. And then the last part that I'm left with is an x times dx. So looking at our earlier work, if I solve for x times dx, I would have du divided by negative 2 is equal to x times dx. So here, replacing my x times dx by negative half of du, well, I can pull the negative 1/2 out in front of my integral, and I've got the following. So this is, of course, much nicer than the integral that we were given. Now, in this example, we see that after we rewrite our integral in terms of u, the upper limit of integration, 0, is less than the lower limit, 16. So we would probably want to reverse these limits of integration or interchange them. And recall, to do that, we would take the negative of this integral. So since we already had a negative 1/2 out in front, this will become a positive 1/2 of the integral from 0 to 16 of the square root of u, or maybe I'll rewrite it as u to the 1/2 power du. So we have our constant 1/2, and now for u to the 1/2, we know how to find an antiderivative. We would add 1 to the power, so we get u to the 3/2, and then we divide by 3/2, which is the same as multiplying by 2/3. And then we're going to take this expression and evaluate at the endpoints, which were 0 and 16. So simplifying a little bit, well, our constants, we have a 1/2 times 2/3, so that leaves us with a 1/3. And then substituting the upper limit of integration to our antiderivative, we have 16 to the 3/2 power minus 0 to the 3/2 power, which is simply 0. So we're left with 1/3 times 16 to the 3/2 power. Now recall, the 3/2 power is the same as taking the number 16 and multiplying by the square root of 16, which is 4. So altogether, we're left with 64 over 3. So in this example, we see if we are evaluating a definite integral of a function and finding an antiderivative requires a substitution, we have to change our limits of integration from x values to u values in order to evaluate that integral. And in some cases, your limits of integration might be in a reversed order from what you would prefer. So we just recall here that we can interchange those limits of integration by making the integral a negative. So let's look at another one, a little more practice. In this next one, we are asked to evaluate the definite integral from 1 to 9 of e to the square root of x divided by square root of x. So this involves a composite function, namely our numerator is e raised to the square root of x, which suggests that we should try a substitution. So our first step will be to choose a value for u. Again, it's typically the inner function in our composition, so in this case square root of x, in which case the differential of u is the derivative. Now the derivative of square root of x is 1 over 2 times the square root of x, and then we multiply by the differential dx. Now again, the integral that we were given was in terms of x, so if we're changing to u, we need to change our x values into u values. So here the values of x, which were our limits of integration, were 1 and 9. Let's see what the corresponding u values are. So if x is equal to 1, then u is the square root of 1, which is 1. And if x is equal to 9, then u is the square root of 9, which is 3. So let's take the integral that we were given from 1 to 9 of e to the square root of x divided by square root of x dx and rewrite it in terms of u. So here we will have the integral from 1 to 3 now. These are our u values. And our numerator, which was e to the square root of x, is now just e to the u power. And then we're left with a dx divided by the square root of x. So if we look back at our previous work, we see that if we have the differential dx and we're dividing by the square root of x, that's the same as 2 times du. If we multiply both sides of that equation by 2, we have 1 over the square root of x dx. So my dx divided by root x becomes 2 du, and I can pull the constant 2 out in front of my integral. So now I have 2 times this definite integral, and for e to the u, we know what an antiderivative is. It would be its own antiderivative, namely e to the u. And once we have our antiderivative, the fundamental theorem of calculus says we evaluate at the endpoints from 1 to 3. So we have our constant 2 out in front. Substituting u equals 3, we have e to the third. Minus, substituting 1 for u, we have e to the first, or just e. So this would be the value for that definite integral.